Hey there, and welcome. Have you ever stopped to think about how everything around us is constantly changing? From the way our bodies get energy to the stars burning in the sky? Well, the engine behind all of that change is the chemical reaction. So today, let's unlock the code behind these amazing processes together. Think about it for a second. A rusty nail and a burning match. On the surface, they seem like total opposites, right? One is this really slow, silent process, and the other is super fast and bright. But believe it or not, they are both playing by the exact same set of rules. And by the end of this, you're going to see exactly how they're connected. So here's what we've got lined up. First, we'll cover the basic rules of the game in the atomic shuffle. Then, we'll dive into the 7 key playbooks that atoms follow in the 7 reaction recipes. After that, we'll see them in action all around us in chemistry in your world. And we'll wrap up with a really handy tool I call the reaction identifier. All right, first things first, before we can start sorting reactions into different types, we gotta understand what's actually happening on a super tiny atomic level. And honestly, it's all just a big, elegant shuffle. So what is a chemical reaction at its absolute core? Well, it really just boils down to 2 things. Breaking the chemical bonds that hold atoms together in your starting ingredients, we call those the reactants, and then forming completely new bonds to create brand new stuff, which we call the products. It's like a total molecular makeover. Now, this right here, this is the single most important rule in all of chemistry. It's called the law of conservation of mass. And all it means is that you end up with the exact same atoms you started with. They've just, switched partners and rearranged themselves. Nothing is ever lost, nothing new is created. It's just a reshuffle. So how can you even tell if this atomic shuffle is happening right in front of you? Well, chemistry gives us some pretty classic clues. You might see a sudden, dramatic change in color. Or maybe you'll notice bubbles of gas fizzing up. Sometimes a solid material kind of just magically appears in a clear liquid. Or you might just feel the beaker get noticeably hotter or colder. These are the telltale signs. Okay, now that we've got the ground rules down, let's get to the main event. The 7 fundamental recipes or playbooks that pretty much all reactions follow. Once you know these patterns, you can start to understand and even predict what's going to happen. First up, we've got the combination reaction. Some people call it synthesis, and it's as simple as it sounds. You take 2 or more simple things, let's call them A and B, and you combine them to build one single, more complex thing, AB. It's the ultimate building block reaction. A perfect example of this is when you burn a magnesium ribbon. It reacts with the oxygen right out of the air in this dazzling, super bright flash of light. The 2 separate elements, magnesium and oxygen, combine to form one single new compound, that white powder magnesium oxide. See? A plus B gives you AB. Simple as that. Next, let's flip that idea completely on its head. We have decomposition. Here, you start with one complex compound, AB, and it breaks down into 2 or more simpler parts, A and B. Now, since you're breaking bonds, this usually needs a little push, some energy, like from heat or electricity to get it started. A huge, real-world example is in making cement. You heat up limestone, calcium carbonate, and it decomposes. It breaks right down into 2 simpler things, quicklime and carbon dioxide gas. One single reactant becomes 2 separate products. Okay, things are about to get a little more dynamic with single displacement. The best way to think of this is like a dance. You've got a couple, B, C, dancing together. Then a more reactive element, A, comes along, cuts in, and kicks B out so it can dance with C. It's all about which element is more reactive. We see this happen all the time when you drop a piece of zinc metal into acid. Zinc is more reactive than hydrogen, so it just swoops in and kicks the hydrogen right out of the acid. What you get is zinc chloride, and the hydrogen is released as a gas. You can literally see the bubbles of that displaced hydrogen fizzing away. So if the last one was someone cutting in on a dance, this one, double displacement, is a full-on partner swap. You start with 2 couples, A, B, and C, D. They meet on the dance floor, their ions decide they like the other partner better, and they just switch. You end up with 2 totally new couples, A, D, and C, B. Combustion. You already know this one. It's just a fancy word for burning. The key ingredient for any combustion reaction is always oxygen. A substance reacts super fast with that oxygen to release a ton of energy, which we see and feel as heat and light. Think of our matchstick from the beginning. And here's a really useful cheat code for you. When you burn hydrocarbons, that's stuff like natural gas, propane, gasoline, the products are always the same, every single time. You get carbon dioxide and water, plus a whole lot of energy. This is the reaction that heats our homes and powers our cars every day. Okay, redox reactions might sound a little complicated, but they're all about one thing: trading electrons. One atom loses electrons, we call that oxidation, and another one gains them. That's reduction. The best way to remember it is with this little phrase: oil rig. Oxidation is loss, reduction is gain. And this electron trading is a huge deal. It's what makes batteries work. And hey, remember that rusty nail from the intro? That's just a classic super slow motion redox reaction. And finally, our seventh type is neutralization. Now, this is actually a special, very important kind of double displacement reaction. When you mix an acid with a base, they react to neutralize each other's effects. And the products are always the same: a salt and good old water. This is exactly how an antacid tablet calms the acid in your stomach. So these 7 recipes, they aren't just for a chemistry lab, you know? They are happening constantly, all around you, and even inside you, right this second. Let's connect what we've just learned to the world we live in. You know, every reaction involves energy. Exothermic reactions are the ones that release heat, making things feel hot, like a campfire, which is combustion. On the flip side, endothermic reactions absorb heat, making their surroundings feel cold. Ever used one of those instant chemical ice packs? That's a reaction literally pulling heat out of the air to get going. And just think about it. Photosynthesis, which gives us our oxygen, is a complex synthesis reaction. Digesting your lunch involves countless decomposition reactions. The very act of breathing, respiration, is a type of controlled combustion. And as we know, rusting is a slow redox reaction. Chemistry isn't just a subject, it's literally life. All right, for our last section here, I want to give you a practical tool, a quick cheat sheet that will turn you into a reaction identifier yourself. You can actually learn to spot these patterns just by looking at a chemical equation. It's easier than you think. This little guide gives you the clues. For example, if you look at an equation and you see only one single substance on the left side of the arrow, the reactant side, you know it has to be decomposition. It's the only one that works that way. Or if you see O2 as one of the reactants, it's a huge hint. You're probably looking at combustion. See? It's all about just spotting the pattern. So what this all comes down to is that chemistry isn't just something stuck in a textbook. It's the invisible script that the world is following every single moment. Now that you know the 7 main plot lines, what reactions are you going to notice today? The browning of an apple, the fizz when you open a soda, the flame on your stove? The code is absolutely everywhere. And now you have the key to start reading it.